Hello! In this tutorial, we will continue to talk about color models in 3D LUT Creator. Let's consider the remaining color models of the program. I will use color gradients again to show how the saturation depends on the lightness in these models. In the LXY model, the L component represents the lightness from the LAB color space. The other two components mathematically represent the coordinates of the projection of the point on the color plane that is perpendicular to the neutral axis on the RGB cube. If you don't know what the RGB cube is, you can watch the video called "What is the LUT?" on this channel. So let's take an RGB cube and draw a neutral axis inside it. Now I turn it so that the neutral axis is vertical. Let's say we have a specified color in RGB color space. Then in our cube, it can be represented by a point. Now we draw through this point the color plane, which is perpendicular to the neutral axis. We construct a coordinate system on this plane and find the projection of this point on the axis. That's how the X and Y components of the LXY model are found. As you can see on the CL grids in the LXY color model, the light and dark tones lost their saturation. It happens in the LAB color model also. The increase of saturation when moving from the shadows to the lights in this model is slower than in LAB. Projections of color gradients on the AB grid model form straight lines, while in the LAB model they look like loops. In the MXY model, the M component is mathematically the length of the vector in the RGB cube, which is directed from the origin to the point with the specified color. Imagine a point inside the cube with a specified color and draw a vector to it. Its length will be equal to the M component. In this case, the set of points for which the length of the vector M is the same form a spherical surface inside the RGB cube. The X and Y components in the MXY model are defined in the same way as in the LXY model. In the MXY model, the saturation also depends on the brightness, which can be seen on the CL grids. But unlike the LAB model, the colors in the MXY model on the AB grid are more symmetrically and evenly spaced. The MXYE model, as you probably already guessed, has expanded saturation of lights and shadows. Let's open the CL grids to see it. In the MABE model, the color saturation in the shadows is even less dependent on the lightness. The A and B components in this model specify the angles between the projections of the vector M onto two mutually perpendicular planes and the neutral axis in the RGB cube. Let's construct two mutually perpendicular planes in the RGB cube. Find the projections of the vector M on these planes, and now we find the angles between the projections and the neutral axis. This will be the A and B components of the MAB model. Since A and B are angles with respect to the neutral axis, even for dark colors, they can take a wide range of values. This allows you to distinguish between dark colors and not confuse them with less saturated colors. For example, in the MXY model, the range of X and Y values for dark colors greatly decreases as the RGB cube section decreases. In the SXYE color model, the S component represents lightness as the sum of the R, G, and B channels, and X and Y are again the coordinates of the projection of the point on the color plane perpendicular to the neutral axis in the RGB cube. This color model also has expanded saturation of lights and shadows. Let's consider the YUV model. In this model, Y is a luminance component, and the other two contain a color. The YUV color space was created for the compatibility of black and white and color TVs when playing a single video signal. Black and white reproduced only one signal, Y, and color TVs worked with all three components. In this color model, the saturation increases linearly to its maximum and then decreases linearly to 0. It is notable for the fact that one of the image analyzers, which is called vector scope, uses this color model. To enable it, I open the Program Analyzer window. You can also meet VectorScope in other programs designed for video color correction. If we open the AB grid, we will see that the color gradients repeat the shape of the gradients on the VectorScope, with the only difference that they are rotated clockwise on the AB grid. If we right-click on the VectorScope, we get a side view of the three-dimensional color body of the YUV space. By clicking and holding down the left mouse button, we can rotate it. That is, on the AB grid, we see a top view, and on the CL grids, we see the side projections from two angles of the color body. By changing the angle of the axes, we can see this body from other angles, as if we are rotating it in a VectorScope. Let's try to change the saturation of the red gradient. In this case, you can see how the color moves on the VectorScope. Now look at the side view. Let me remind you that VectorScope always works in YUV space and does not depend on the chosen color model. Two color models remain, CMYK and RGBW. Both models have four components. In order to display these models in three-dimensional form, they were reduced to three components. Let's look at how. The CMYK model is a subtractive color model, which means the higher values in C, M, or Y channels we use, the darker the color. Then to get the black color, we need to use all three components at the maximum, and this is inconvenient since ink spoils while printing. Therefore, the K channel that contains black ink was added. This is how the ideal CMYK model works. In reality, there are many more nuances. Now let's see how to bring this model to three components. Let's say we have a color C55, M12, Y8, K12. If we assume that an equal amount of paint in all three color channels is black, then this amount can be subtracted and added to the black channel. In this case, this component is 8. As a result, we get C47, M4, Y0, K20. That is, in this case, the yellow has become 0 and cannot be used in the construction of a three-dimensional body. In general, one of the three color components, C, M, or Y, can be made to be 0. The RGB model is an additive model. That is, the higher values in the channels, the lighter the color. To get white, you need to use all three color components at the maximum. If we assume that an equal amount of color in all channels is white light, then this amount can be subtracted and added to the new channel W, which will represent only white light. As a result, we get only three components that are not equal to 0, which can be used to construct a three-dimensional body. This is how the RGBW model works in 3D LUT Creator. Now let's see how the color gradients look in these models. In the CMYK color model, when moving along the color gradient from the shadows to the lights, the saturation on the CL grids is constant until I reach the region with the maximum saturation on the color gradient. Then the saturation linearly drops to 0 on the CL grids. In the RGBW model, when moving along the color gradient from the shadows to the lights to the maximum point, the saturation increases linearly. The brightness equals 0. And after reaching the maximum, the saturation is constant. Comparing the working color models, it is also necessary to note how they transmit the luminance component of the image. This image shows red, green, and blue colors with the maximum value of each color in the corresponding R, G, and B channels. If we evaluate their brightness from the side of visual perception, then the green circle appears the brightest, the red circle is darker, and the blue circle appears to be the darkest one. Now we reduce the saturation to 0. As we see in the LAB model, the green color remains the brightest, then goes to red, and the darkest one is the blue. The same happens in the LABN and LXY models. The models of the HSP group also take into account this feature of the perception of color by human vision. In the YUV model, this is also taken into account. Other models do not take this into account, so the brightness does not depend on the specific color. These are models starting with M. the SXYE model. Also, this is true for the CMYK and RGBW models. And now, let's see how color gradients with zero saturation will look in different color models. That's how they look in the LAB model and other LAB-based models. Here are the models starting with M. There will be a slight difference in the SXYE model. That's how the color gradients will look in the HSP-based models. Let's change the model to CMYK. Pay attention, as I mentioned earlier, from the place on the gradient, where the color takes the maximum saturation, and to the light tones we lose details, since the lightness will be maximum. In the RGBW model, when we move from the shadows to the point with the maximum color saturation, we also lose details, since the lightness in these sections is 0. And now choose the YUV model. Here's what we had before, and that there is the after. Let me remind you that this gradient was made in Photoshop by blending the color stripes to the monochrome gradient in the color blend mode. Now we have done the reverse procedure. These features can be taken into account, for example, when transferring images to black and white by reducing the saturation and selecting a color model. In general, the choice of the desired color model will depend on the goal that you want to achieve while doing color correction. Now, knowing how to analyze color models with the help of the test images, which can be downloaded from the 3DLUTCreator.com, you can do it by yourself. I hope this video was useful. Subscribe to the channel. Put likes if this video was useful for you. See you in the next video.